Right. So today we want to look at dynamic programming. In fact, we have like two main topics to be done. This is one of them. And then um, on Saturday morning, I want us to have another meeting to look at the last topic and also go through the areas for exams. Okay. So today we want to look at dynamic programming, also known as deep. Okay, so you hear people in the field of programming saying DP. Okay, basically mean dynamic programming. Now, it's a very key concept in data structures and algorithm. It's one of the hard problems to solve. Okay, and it's mostly used as interview questions or questions when you have interviews in a programming space or problem solving space for computer science students. Okay, so let's go into it. Okay, so what is, I hope you can all see my screen.
Yes, sir.
All right.
No,
All right, so let's go on. Um, so dynamic programming, what is it? Someone will ask, is it also another programming language? Has it got something to do with programming? Okay. So just a moment. All right. So dynamic programming is a technique in computer programming that helps to efficiently solve a class of problems or a group of problems that have overlapping sub problems and also an optimized structure, substructure property. Okay. What it simply means is that it is a method or a technique in programming that helps you to solve basically problems faster by remembering some past results, okay, instead of trying to recalculate them every time. So they come, you have a what we call a sub problems or a group of sub problems, and then they might be overlapping each other. Okay. And even in that, there's always an optimal property to solving that problem. Now, there are two main, um, there are two key principles when it comes to dynamic programming. Okay. One of which I've mentioned in here, we have the overlapping sub uh, overlapping sub problems, and then we have the optimal substructure. Okay, so these are two fundamental properties that we consider when dealing with dynamic programming. Now, dynamic programming is mainly an optimization problem rather than recursion. Okay, and we learned recursion some few weeks back, where we said a program trying to run itself. Okay, so wherever you see a recursion problem that has repeated calls for the same input, we can optimize those problems using dynamic programming. using dynamic programming. So dynamic programming, the idea is to simply store results of SAP problems so that we do not have to recompute them when we need them later. Okay, so we do not have to recompute them. Like I said, you are solving problem faster and trying by remembering some past results. Okay, instead of always trying to recalculate or recompute them each time. So it says here, for instance, if any problem can be divided into sub-problem, which in turn are divided into smaller sub-problems, and if they are overlapping among these sub-problems, then the solution to this sub-problem can be saved for future reference. It can be saved for future reference. Now, in this way, efficiency of the CPU can be enhanced. And this method of solving a solution is referred to as dynamic programming. Now, let's look at this example. The last time we talked about the Fibonacci series. Now, to find this sequence up to the fifth term, okay, so we know the sequence 0, 1, 1. We add 0, you start from 0, then 1, you add 1, you get 1. You add 1 and 1, you get 2. You add 1 and 2, that gives you 3. Okay, you add 2 and 3, that will give you 5. That's how the Fibonacci sequence is implemented. So this is saying a sequence up to the fifth term. So this gives us the fifth term. Now it says each number is the sum of the two preceding numbers. So just like I explained, and this is the algorithm, which is a recursive approach to answering this, solving this problem. If you don't remember what we learned from it, you can always go back to the video on introduction to algorithm and the analysis of algorithm. We talked about the recursive uh, approach or recursive algorithm. So in the Fibonacci example, the first term is 0, the second term is 1, the third term is the sum of 0 and 1. Okay, where 1 is the next step, which will give us 1. And the fourth term is the sum of the third term and the second term, which is 1 plus 1, giving us 2. And then the fifth term is the sum of the fourth term and the third term, okay, from step 3. That is giving us 2 plus 1, which is 5, which is 3. So that's the Fibonacci sequence. So it's explained here. Now let's break down how this dynamic programming work. Now, if I mentioned that there are two key principles or two key properties. The overlapping sub-problem. The overlapping sub-problem simply means that or a problem has overlapping sub-problem when the smaller task is solved multiple times. Okay, when the smaller task is solved multiple times. So for instance, the Fibonacci numbers or sequence we just saw is making use of the overlapping approach. Okay, so what is happening is that you are computing using the recalculating using the old or like the way the definition says, you are recalculating it, okay, or recomputing. I think the word used there was Yes, so you don't have to recompute. So we are recomputing. If you look at the approach, we are using the same logic to do the recomputation. Okay, so that's a typical example when we talk of the overlapping problem. Then we also mentioned that there's the optimal substructure. The optimal substructure, uh, if a problem has an optimal substructure, it means that that's the best solution to the bigger problem. Okay, and it depends on the best solutions to the smaller problems. So, for instance, the short path from maybe uh, part, moving from, let's say, A, B, C, D, moving from A to D depends on the shortest path from A to C, okay, before you arrive at D. All right, so how does dynamic programming approach work? It says that it breaks down the complex problem into simple or simpler sub-problem. It finds the optimal solution to these sub-problems. Now, it stores the results of the sub-problem known as memoization. Okay, memoization, not memorization. So there's no R here. Okay, memoization. And this memoization is the process of storing the results of sub-problems. That's storing the results of the sub-problem. First, take note, it's broken down into a sub-problem. Then we find the optimal solution of these sub-problems. And then the results of the sub-problems are stored. Then it reuses them so that the same sub-problem is calculated more than once. And then finally, we calculate the result of the complex problem. Calculate the result of the complex problem. So dynamic programming is applicable to situations where uh, uh, you have these properties. So the overlapping subproblem and the optimal substructure, where optimal substructure means that the solution of the optimization problem can be obtained by simply combining the optimal solution of the subproblem. In the case of dynamic programming, the space complexity would be increased. So we are storing would be increased as we are storing the intermediate result, but the time complexity would be decreased. Now, there are two approaches to dynamic programming. There's the top-down approach, which is known as the memoization techniques. And then there's the bottom-up approach, which is known as the tabulation technique. So let's look at the first one, the top-down approach. Top-down approach simply has to do with you thinking and remembering your answer. Okay, so top-down approach follows the memoization. Memoization. Yeah, I made a mistake here. Yeah. So the top-down approach follows the memoization technique, while the bottom-up approach follows the tabulation technique. Memoization is equal to the sum of recursion and caching. Okay, so for instance, what you do is you solve the big problem first, and whenever a smaller problem appears, you check if uh, uh, you have solved it before. If yes, you use the stored answer. If no, if you've not solved it before, then you solve it and then store the result. Okay, so a problem, you have a bigger problem, and then you solve the bigger problem first, and then whenever the smaller problem comes, you check if that problem has been solved before in the bigger problem. If it's not been solved before, then uh, uh, you if it's been solved before, then you store it. If it's not been solved before, then you solve it and then store the result. So recursion means calling the function itself, what caching means storing the intermediate results. Storing the intermediate results. All right, let's go on. So the some advantage of the top-down approach is that it's very easy to understand and implement. Like I said, you would have solved that big problem first, and then whenever a smaller problem comes, you see if it's already stored. If it's been solved before, then you store the answer. If it's not, if not, then you have to solve it and then store the answer. So it's easy to understand and implement. It solves the sub problems only when it is required, and it's easy to debug. Then with the disadvantages, it uses the recursion technique that occupies more memory in the core stack. So sometimes when the recursion is too deep, the stack overflow condition will occur. Then it also occupies more memory that degrades the overall performance. Okay, so that's one the disadvantage with the memoization technique, which is the top-down approach. So this example here, looking at how the top-down approach works. So it says here, so basically with the uh, Fibonacci numbers, if you take the number, says if the number is less than 0, then it's error. If it is equal to 0, then it will return 0. If it is equal to 1, it should return 1. And then find the sum, okay, of the first term and the next term to give you the uh, to give you your Fibonacci numbers. All right, let's go on. Then we have the bottom-up approach. Like the way I said, the bottom-up approach uses the tabulation techniques. Now, the bottom-up approach is also one of the techniques which can be used to implement dynamic programming. It uses the tabulation technique to implement the dynamic programming approach. It solves the same kind of problem, but it removes recursion. Okay. So whereas the top-down approach, okay, is making use of recursion, the tabulation method or the bottom-up approach removes recursion. So if we remove recursion, there is no Stack Overflow issue and no overhead of the recursion function. In this tabulation technique, we solve the problem and store the results in a matrix. Okay. So for the memoization technique, it's basically like you are keeping a notebook for answers. Okay. So it's like you're just keeping a notebook for answers. You are writing the things in it. However, the bottom-up approach is looking at thinking about the build-up solution from the smallest sub-problem to the biggest problem or to the big problem. Okay, so you start with the smallest cases, you combine them until you reach your final answer. And these are usually done using tables and array. Okay, and it's just like you are building a house with brick. So you start from layer to layer, brick by brick, okay, as you build. Now, the bottom-up approach, the bottom-up is the approach used to avoid recursion. That's saving the memory space. The bottom-up is an algorithm that starts from the beginning, whereas the recursive algorithm starts from the end and work backwards. In the bottom-up approach, we start from the base case, find the answer for the end. Okay, so the base case, the Fibonacci series are 0 and 1. Those are the base cases. Since the bottom approach, starts from the base case, so we will also have to start from 0 and 1. So we solve all the smaller sub problems that will need to be solved, that will need to solve the larger sub problem, then move to the larger problem using the smaller problems. So we use the for loop to iterate over the sub problem. And we said the bottom up approach is also known as the tabulation or table filling method. So this is an example. So it says here that suppose we have an array that has 0 and 1 values at index 0 and index 1 position, respectively, as you can see below. Since the bottom-up approach starts from the lowest or the lower value, so the value at 0, A0 and A1 are added to find the value at A2. Then the value of A3 will be calculated by adding the value of A index 1 plus A index 2, and then it becomes 2. It becomes 2, as we can see below. So this is the approach, this is the difference. So there's divide and conquer approach, which is also different from dynamic programming. So divide and conquer approach requires 3 steps. You divide, you conquer, and then you combine. But the dynamic programming involves a sequence of 4 steps, which is characterized by the structure of the optimal solution. So the recursively define the values of the optimal solution, compute the values of the optimal solution from bottom-up minimum, and then construct an optimal solution from the computer information. Divide and conquer is recursive. Dynamic programming is not recursive. It does more work on sub problems. The recursive solves problem only once and stores the value in the table. Divide and conquer is a bottom-up approach. It's a top-down approach. Dynamic programming is bottom-up. Divide and conquer are independent of each language. And then the dynamic programming sub-problems are dependent. That's how come on they are dependent. So some examples here we have for the divide and conquer merge sort binary search. We talked about the binary search most especially. And then example of dynamic programming, we have matrix multiplication. It's just a moment. All right, let's go on. So some types of dynamic programming algorithms. Dynamic programming algorithms. So we have the longest common sequence. There's also the longest increasing sequence. There is matrix chain multiplication, longest palindromic sequence, cutting a rod problem. There's Floyd, Wassel algorithm, Dutch national flag, 01 knapsack problem. Okay, and a few other problems that are classified under dynamic programming. So let's focus on one. For today, when you go further in this course, I believe you'll be exposed to other aspects of the dynamic programming problems or algorithms. So let's look at longest let's look at the longest common sequence. Longest common sequence. So longest common sequence is defined That's the LCS. Okay, so it's defined. So the longest common subsequence is defined as the longest subsequence that is common to all the given sequences. Okay, so provided that the elements of the subsequence are not required to occupy consecutive position within the original subsequence. Okay, so basically you have um, the longest common subsequence is a classic problem in dynamic programming. Okay, so first and foremost, it's a classic problem in dynamic programming. Now, it is a subsequence in a sequence that appear in the same order, but it is not necessarily next to each other. Okay, so we will see some examples to explain. So for instance, it says if S1, okay, sequence or subsequent S1 and subsequent S2 are two given sequences, and Z is the common subsequence of S1 and S2. If Z is a subsequent of both S1 and S2, okay, so Z is a common subsequence of S1 and S2. If Z is a subsequence of both S1 and S2. Furthermore, Z must be a strictly increasing sequence of the indices of both S1 and S2. Okay. Now, in a strictly increasing sequence, the indices of the element chosen from the original sequence must be in increasing order of Z. Must be in increasing order of Z. So over here, we say if S1 is B, C, D, A, C, D, okay, then A, D, C, sorry, A, D, B cannot be a subsequence of S1, okay, as the order of the element is not the same. Okay, so it's not strictly increasing sequence. Okay, so what it means is that when we look at the order of this sequence, okay, and we look at this subsequence, you can clearly tell that A, which if we take A, let's say this is the first element, A, and we try and trace the sequence, you can tell it's not in the same order as the subsequence we have here, because the subsequence is saying ADB, and it's not in that increasing order. Okay. Then we have another sequence. We have another sequence given here. We have S1 and S2. All right, let's go on. So we have here S1 and then S2. We have here S1 and S2. Or let me just give another example before we come to this. So let's assume we have a string. Let's assume we have a string, and the string is, or the sequence is A, B, C, D, and E. Okay. Now, Please, are you all following me? Are you all with me?
Yes, sir.
All right. And you are given A, B, E. And A, C, E be considered as a subsequence. Anyone?
Yes, sir.
Okay. All right. Yes. So ACE, sorry, can be considered as a subsequence because what is following in that order: A, C, and then E in that order. What about B, BDE? Can we consider BDE as a subsequence of?
Yes, sir.
Yes, who is responding? Is it Theophilus?
Yes, sir.
Is it a subsequence?
Yes, it is.
Okay. So that's also a subsequent. What about AEC?
No, sir.
No, sir.
Okay. So AEC is not a subsequence. Okay. It's not a subsequent. That means the order has changed. It's not following the order of this subsequence we have here. All right. So let's come to this example. So in this example, we are given two strings or two sequences. We have the first sequence S1 or string S1, BC, CD, and then we have sequence 2, which is AC, AC. Now, the common subsequence from this are given here. We can have what's BC, right? If we take this, we can have BC. When we come to sequence 2, we can have B here and C here. So this subsequence qualifies. Are you with me? I hope you are following.
Yes, sir.
Yes, sir.
Okay. Now, the next one is saying C, D, A, C. Is this subsequence here common to S1 and S2?
Yes, sir.
So if we take the first S1, we can see here C, we can see D, we can see A, and then what? C again. So it's common, it's a common sequence, or it's a sequence, it's a subsequence in S1. Now let's go to S2. S2, we have what? C here, there's D, there's A, and then there's C here. So this is also a common subsequence for both. Then let's go to the next one. We have DAC. So we check for both S1, D is here. We have D here. There's A. We can choose this A. And then C. Okay, so it's a subsequent for S1. Let's check S2. S2, we have D here. There's A here. And then there's C here. So this is also a common subsequence. Okay. So in a question, in a problem like this, you can be asked to list the common subsequence given a string, two strings, S1 and S2, or even it can be more than that. And you are told to list the common subsequence among the list. It's easy to get it, right? Are we all here?
Yes, sir. Yes, sir.
Okay. Now let's move to the more interesting aspects of this problem. Now, after getting the common note, we are looking at what? longest, right? Longest subsequence. So far, what we've done is to look at the common one. Okay, so once you get all this as common, and you can get more. Okay, so you can get more. So over here, it says that among this subsequence, CDAC is the longest. Emphasis on the longest. If you say the longest, what it means is that the one with the highest number of strings. All right, sorry, let's go on. So the common subsequence, okay, yes, these are the common subsequence, but we are looking for the longest among them. And this happened to be the longest subsequence. Okay, this happens to be the longest subsequence. There are times you can get more than one longest subsequence given a particular string. So if you are talking about the longest subsequence, we are talking about the length of the elements or characters. Okay, so the length of the string. So when we take this will give us a length of 4. Okay, this will give us a length of 4. So there are also times where the fact that is giving you that length of, let's say, 4 or 3, and you are getting about 2 of them, it doesn't also mean that the the all the 4 or all the 3 are your longest subsequence. Okay, so you can get it, which is a sub problem. Okay, however, you can have one of that longest common subsequence being the optimal one. Okay, so we talked about the properties. So it has to be optimal. So not just that, okay, we have about 2 or 3 of the 2 or 3 of the common subsequence, okay, which have a length of, let's say, 4. Okay, now out of those 2 or 3, you need to check for which of them is optimal. Okay, which of them is the optimal substructure or subsequence from that. Now, this LCS is important because it helps in doing things like DNA sequence matching, helps in file comparison of files. It helps in spell checking, okay, and also plagiarism detection. So these are some of the techniques that are used in some of these application or experiments, okay, that you know of, things like DNA sequence matching, plagiarism detection, file comparison, spelling checking, and also, for instance, in even programming, using version control, using of Git, and so on. Dynamic programming with the use of largest common sequence. It's important when it comes to those examples. All right, so based on the question I asked, how are you able to determine which of the longest or which um, longest common sequence among the longest common sequence that you have is optimal? Okay, now you can solve this by using the tabulation approach to find the optimal subsequence. Okay, by using the tabulation approach. Now, you can see here, it says, let's take these two sequence, AC, ADB, that's the X, and then the Y sequence is given as CD, AD. Then it said create a table of dimension n+1 by m+1, where n and m are the length of X and Y respectively. So if we take X has a length of what? What's the length of X? Who can tell us?
5.
The length is what? 5. Okay, so this is n. N is equal to 5. What about the length of Y?
4.
It's 4. So n+1 will give us what? 6. And then this +1, n+1 will give us 5. Okay, so we draw this table. So that means 6 by what? 5. A table, or a 6 by 5 table. That's 6 rows by 5 columns. 6 rows by 5 columns. Okay. Now, when you draw the table, the first row and the first column are filled with what? Zeros, as you can see here. The first column and the first rows are filled with 0. Are you following?
Yes, sir.
Then we let's move on. Now it says, sorry. It says fill each cell of the table using the following logic. If the character corresponding to the current row and the current column are matching, so there's some logic here which you need to understand in order to be able to fill the table. Okay, so it said if the character corresponding to the current row and the current row and the current column are matching, then you fill the current cell by adding 1 to the diagonal element. Okay, and then point an arrow to the diagonal cell. Okay, then else, that is otherwise, if they are not matching. So if we take cell A and the first cell, the first letter, character in X, and the first character in Y, if they are matching, then we execute the first part. which is this part. Okay. However, if we take these two and they are not matching, then we execute the second part. And what's the second part saying? It's saying that else take the maximum value of the two. So we look at this and this, and we take the maximum value. So initially, we are starting from 0 throughout. However, the values may increase as and when we keep adding 1. Okay, like he's saying here. There are points where we will add 1. In this context, the other alternative, when the values are not the corresponding values are not matching, then we find the maximum among the two corresponding value from the maximum from the previous column and then the previous row element. Then we fill the current cell. So we point the arrow to the cell with the maximum value if they are equal, and then point to, if they are equal, we point to any of them. Okay. Oh, all right, sliders. Okay. Oh. All right, so step 3. So we have to repeat step 2. Okay. So the whole table is full or is filled. Now, this is what it's trying to say in step 2. It says that, so we start by making all the rows, all the columns 0, and all the rows also what? 0. Are you following?
Yes, sir.
Then we take the first element here, or for the X, this is your X, this is your Y. So we take these two corresponding value, the characters, and we find out, are they the same? Okay. Are they the same? Is A the same as C? I need your response.
No, sir.
Oh,
Okay. So if it is no, then it's saying that if it is no, if they are different, then for this is the cell for which we are trying to input the value. So if it is no, we'll look at the adjacent, the previous cell for A, and then that of C. Okay, the adjacent cells, and compare this 0 here for the A part to the C part, the 0 here. Okay, we'll compare and then find the largest of the two values. So if we take this and this, what's the largest? The largest is still what? 0, right?
Yes, sir.
So we have 0. So if we have 0, then it says what? You should have an arrow what? Pointing upwards. Okay, so point an arrow to the cell with the maximum value. So to the maximum value. So in this case, it's pointing upwards. So assuming the maximum value is the one up. Then we come to the next cell. We come to the next cell, which is this. Now, if you take this 2 cell, if you take this, okay, we have what? A and what? B. Are they the same?
No, sir.
So if they are not the same, we take the previous one, which is 0, and then compare it to the one on top, which is the B1, which is also 0. And then we find the highest. So the highest will also be what? The maximum will be 0. Okay, the maximum will be 0. Then we move to the next one, which is this cell. So in this cell, we have A and what? D. So A and D, are they the same?
No, sir.
They are not the same. So if they are not the same, we take the previous one for the A, which is 0, and then the D, which is also 0. Then we find the maximum between these two, and that will also give us what? 0. Okay.
Sir, please, I have a question.
Yes, you can go on with your
Okay.
question.
So the last part of step 2 is saying that if they are equal, you point the arrow to any of them. That's
Yes.
any of the maximum number is equal. If they are equal, you point it
Yes.
to any of them.
Yes.
So looking at the some example that we are doing right now, you see the arrow is pointing to the
top.
up one, which is
Yes.
So it can also be pointed to the other one, which is for A.
Yes, exactly. It
Okay.
can be pointed to
Thank
the
you.
left.
Okay, thank you.
Yes. Yeah. Okay, so I think that's a good question. So let's take the next cell, which is what? A, and then what? A. Are they the same?
Yes, sir.
Yes.
So if they are the same, what's the rule saying? It said if they are the same, there should be what?
You add one.
A letter pointing. What did he say? Let me go back to get what it says. So it says, if the character corresponding to the current row and the current column are matching, then fill the current cell. So in this case, it will be the red cell, right? We are filling it by adding 1 to the diagonal element. To what? The diagonal element. Okay, so let's go back to the slide. So when we fill it, so this is the diagonal element, this is the cell. Okay, and the characters are the same. The corresponding characters. The corresponding characters are the same. So A and A. So if they are the same, then we look at the diagonal cell, which is this one. So I'm circling it red. That's the diagonal one. Okay, and then we add 1 to it. So when we add 1, now in the red cell, we have what? 1. You get the logic.
Yes.
Okay.
No,
So
sir.
let's repeat it for this one. Let's repeat it for this one. So
Sir,
over here. Yes.
Let's not forget that we will point the arrow to the diagonal.
Yes. So this is the
cell.
arrow. This is the arrow.
Okay.
So let's take this one. So this one, we have C and C. Are they the same?
Yes.
No.
Who is saying no? Is the person for
Yes, they are the same.
No, it's not.
So C is here. So let me wipe. Okay, let me keep the color codes here. So I'm using brown now. So we have C and C here. We are looking at this cell. So C, this, and then this cell. Are they the same? Are the characters the same?
Yes,
So
they are the same.
if they are the same, Then what are
Look
we
at the
supposed to do?
diagonal cell.
We look
We
at the
look at the
diagonal,
diagonal cell.
which is what? 0.
0. Then we
So
add
what do
1.
we do to it? We add 1 to
We
it,
add 1.
and then this cell will now be 1. Okay. Then we move to the next. We move to the next cell. I'll use a deeper green. So we come to this cell. So we are still looking at C. And then this is what? B.
B.
Are they the same?
No.
They are not the same. So
Yeah.
what do? We compare this one here and then the
And then-
0 here to see which
we
is
look
the
for
maximum.
number.
The
Yes.
maximum number is 1. So we'll
1.
put here 1. And then we'll put
And the
our
arrow
arrow
should be on 1.
to be on 1. You get it?
Yes, sir.
Please, are we all here?
Yes, sir.
Yes, sir.
Okay. Then we move to the next cell. I'm trying to use different colors so that you understand what is happening. So the next cell is purple, the purple cell. We are still on C, and this time E. C and D, are they the same?
No, sir.
They are not the same. So if they are not the same, we find what? This
The
cell
maximum.
and this one, and we check for the maximum. So the maximum is what? 1. So we put 1 here, and then we move the arrow to point towards that one. Are we on track?
Yes, sir.
Yes, sir.
Okay. So let's do for the last cell. Let's do for the last cell. So we come to the green cell. The green cell, we have C and what? A. C and A. So C and A, are they the same?
No.
No, sir.
If they are not the same, we look at this one here and the one on top of the cell. We compare and find the maximum. They are equal. So we have what? 1.
1.
So we can decide to move the arrow up. Okay, or we can also decide to move it to the left. Okay, so that is what has been completed here in this table. Can you see that?
Yes, sir.
So if you follow the same logic, if the letters are the same, the characters are the same or otherwise, that should lead you to complete what? The table in this form. Okay. Then the step 4 is saying that the value in the last row and the last column is the length of the longest common sequence. So anytime you finish, the value in the last row and the last column would always give you the longest common sequence. Okay. Now, by observation, if we just look at X and Y, and we are told to deduce the longest common sequence, we can talk about what? Who can guess what would be some of the longest common sequence we have here?
CD.
Anyone? We can have CD. Sorry, let me write it well.
CB.
We can have C what?
CB.
CB.
CA.
We can have CA. Is that all?
Can have. That's all.
Okay. So with this, you can tell that the longest common sequence we will have is what? 2. Because we can't have more than 2. By observation, none of the sequence here from even what we mentioned can give us what? A length of 3. Okay. So that's one way you can check whether your table is correct. If your last row and your last column has a length, okay, which is equal to when you observe and you list them. So in this case, 2 from the table, and then by observation 2, we have what? 2. So that gives us the longest common sequence. Okay. Now let's move to step 5 and see what is happening there. Now, in step 5, we do what is called backtracking. In step 5, we do what is called backtracking. Then the backtracking leads us to get the optimal longest common sequence. Okay. Now, in our backtracking, it says, in order to find the longest common sequence, start from the last element and follow the direction of the arrow. Now, the last element corresponding to the bracket symbol, okay, form the longest common sequence. Now, basically what it's saying is that it also, when you are doing the backtracking, it also has what we call, it also has two logics, okay? You always start from the last cell. Because that's what is giving us the longest common sequence. Okay? We are starting from the last cell. Okay? Now, if you look at this carefully and you are following the arrow, that's another way to help you get the longest common sequence. So whilst you are drawing it, whilst you are filling the table and drawing the arrow, when you get to this point, it makes it easier. But if you don't draw the arrow, then you have to use the backtracking logic to be able to complete it. Now, the logic is the same as the way we fill the table. Now, in the backtracking logic, if the characters are the same, then you have an arrow pointing diagonally, like we can see here. Okay, so we see that this is A, and this is also A. Okay, if the characters are the same, for instance, we can see C here. Here is also C. So anytime we see those, we see what? An arrow pointing what? To the diagonal cell. Can you see that?
Yes, sir.
When you see B here and B in this row, you can see what? In that cell, there's an arrow pointing upwards. When you see D here and you see D here as well, you see that what? The arrow goes up. Okay. You see A here, you see A here again. You can see the arrow going diagonal. And like I said, if you've drawn this arrow when doing step 2 and step 3, then you don't have, it becomes easier when you are finding the largest common sequence. However, if you've not done it, it becomes a bit difficult to tell what is the largest common sequence. Are we clear? Hello?
Yes, sir.
All right, so let's come back to how to determine the largest common sequence. In fact, the optimal one. Okay. So we can tell that this 2 is going upwards. Now, if it goes upwards, it means that they are different. Okay, if they are different, it goes up. These ones are different, it goes up. So what happens is that the A starts from here. Okay, so you start from, you only capture, when you want to find the longest common sequence, you only capture the parts where they are diagonals. So I drew the diagonals earlier. However, you capture the parts where they are diagonal. So for instance, this, okay, we saw the sequence as what? You guys mentioned it. You said C, CD. Someone also mentioned CB.
CB.
And someone also mentioned CA. This is what you see by observation. But if you go to the table approach, you realize that from here, if you are following the arrow, from this, you go to this, which is A, and that's where you have the diagonal. So you capture your A down. Okay, so we are backtracking. Then when you come diagonal, the arrow is pointing to what? The left, all the way to this cell. Then this is the cell which also gives you an arrow pointing what? Diagonal. And that's cell what? C, CC. So you have C. So the optimal longest common sequence here is CA. Okay. Now someone will say, why not CB? Now CB would only work if in the context of drawing the arrow when they are different. Remember, we have to draw an arrow when the when the characters are different, but the comparison, the maximum values are the same. You remember, right?
Yes.
Okay. And you remember that we're always drawing the arrow upwards. So you can see that here 2 and 2 are the same, even though the characters are different. However, the arrow went upwards. Now, if the arrow had gone to the left side this way, instead of going upwards, if we had gone this way, you notice that now we have what? B, right? Then if we take this cell, B and D, they are also not the same. So we have to find the maximum of 2 and 2. We have to find the maximum of 2 and 2. So that one too, instead of going up, we go towards the left. Now, when we go towards the left, we'll end up having this. And this will now give us B and B. They are the same. So we will have the diagonal here. Okay, so that will now give us what? B. We are backtracking. That will now give us B. So the diagonal is leading us to this. Okay, so with this one, if we look at this particular cell here, we have 1. Okay, now this is D and B. They are not the same. So if they are not the same, we look at 1 and 0, which is the maximum. 1 is the maximum. So we are going up. The same applies to this. We are going up. And then this will lead us to this cell, C and C. And we have a diagonal here. So this will give us the optimal of C, of CB. Do you get the logic? So depending on how you draw the arrow, when it's saying that when the values are equal, it says what? If they are, let me clear this. So it said, the else means that you have maybe A and then the next one is C. They are not the same. So it said, else take the maximum from the previous column and the previous row for filling the cell. Then point the arrow to the cell with the maximum value. Now, if the values are equal, that's the previous row and the previous column, if they are equal, then point to any of them. Do you get it? Point to any of them. So that is what is leading to the different answers we are having. So if I look at your table, depending on you pointing to this side, pointing here, instead of pointing up, you point here, it comes here, diagonal, it goes up and comes here, and then goes up here. Then in your case, your optimal or your longest common distance will be C, B. Are we here? Hello? Yes. Any question? So when you
I have
go
a
online,
question.
there are videos on this, simple ones you can watch with different examples to understand the longest common
Please, I have a
sequence.
question.
The longest common sequence. Okay. Yes, Edward.
Okay. So right now that we know, so it's possible that depending on my arrow, I might get different answer for my optical subsequent common subsequence.
Yes. But whatever
But
answer you get should fall within. You remember we gave out three common.
the sub, yes.
Three subsequent. So
So
whatever answer you get should be one of the three.
the three.
Yes.
Oh, okay.
Should be one of the three.
Thank
Okay.
you.
So for instance, let me just see if we have enough time. Let me go through so the first one we got was what? CA, right? The second one was
Yes,
CB.
CB.
So let's look at the
And then
CD one. So if someone is going to get a CD, that means when the person is coming from the last cell, instead of choosing instead of choose an arrow going up, the person decides to choose these two rather as the maximum. Then if it takes these two, D and B are not the same. So it's looking at this two and then this two, but decides that he'll go for the top one. Can you see that? For the B one, we came to the left. Okay. So decides that you go for this two. So when he goes for this two, now we have what? DD. So D will now give us a diagonal because they are the same. Then when he gets here, whichever approach he decides to use, maybe to go up and then to come to the left, he will now appear in this cell, CC. Okay, so the CC, so first this one here will give you the D.
DD. Yeah.
This will give you D. Then when it goes up, he will now end up in this cell, CC. So that will also give you the CD.
CD. Okay.
So it's how you which of the previous either row or column you choose if they are the same. Okay, whether you choose to go up or go to the left, whichever one you choose, if the previous values are the same, that would determine what you get as your final longest common sequence. Okay, so always have in mind, always try and list the common, if you're able to get maybe the last cell, the number in the last cell, always try and list out the common by observation, just lift out just list or outline the common subsequence in your string. Then you can use that to guide you to the longest common subsequence. Okay. All right. So there are some examples here for you to try. Okay, using the length table formulation. So you have 3 of them here. I'd want you to try them. Then there's another example, rod cutting. I wouldn't go much into this. I'd want you to read on your own. So it's a given a rod of n inches and an array of price, which contain array of price that contain the prices of all the pieces of size smaller than n. Determine the maximum value obtainable by cutting the rod and selling the pieces. Okay, so for example, you said the length of the rod is 8, and the values of the different pieces are given as follows. So you are supposed to cut the rod to get a maximum value of 22. Okay, so by cutting the rod to 2 pieces of length 2 and 6. Okay, so 2 and 6, how are you going to cut them to get a maximum, which will give you a value of 22? A value of 22. So this is how the rod cutting example looks like. You have the length, you have the length 1, 2, 3, 4, 5, 6, 7, 8, and then you have the price. So for length 1, if you have a rod, and they say if the length is 1, so 1, 2, all the way to 8. So if you have a length of 1, a length of 1 is maybe 1 Ghana cedis. A length of 2 is 5 Ghana cedis. A length of 3 is 8 Ghana cedis. A length of 8 is 20 cedis. Okay, now the problem is saying that you want to get a maximum length of price. Okay, 24 Ghana cedis. So if the prices are as follows, then the maximum obtainable value is 24 by cutting the 8 piece of length 1. So you are cutting it as to get a maximum value. I think this is related to the previous example. Let's go back. Okay. So the previous example, which was saying that you should get a maximum length of what? A maximum price, right? A maximum value, that's the price. The price should be 22. How are you going to cut it? So you are going to take a rod of length 2, which is this one. So a rod of length 2 will give you a price of what? 5. And then if we take a rod of length 6, so length 6 will give you a price of what? 17. Are you following?
Yes, sir.
Will give you a price of 17. So 6 plus 7, sorry, 5 plus 17 is what? 22, right?
Yes, sir.
Okay. So that's what it's explaining the previous part here, which is saying that, for example, if the length of the rod is 8, okay, and the values of different pieces is given as follows, then the maximum obtainable value is 22. So that 22, how do you get it? By taking 2 pieces of what? 2 and then 6. That's length 2 and then length 6. So basically in this kind of problem, now this is one of the problems. Okay, I think I listed a couple of dynamic problem solving algorithms or problems. Okay, so we have the longest common sequence, which we looked at. Then there's the rod cutting. I'll advise that you read on the matrix chain multiplication also. So if you are going further in computer science, it's also one of the techniques you should know, okay, when you're advancing in data structures and algorithm, the matrix chain multiplication. Now, this helps you in programming languages like Python, MATLAB, and a few others, if you understand this concept. All right, so I think we'll end it here. If there's no question, we'll end the class here. On Saturday, we are going to look at our last topic. I'll give you the slide ahead of time. I'll share it with your rep. The last topic, which is greedy algorithm. Which is greedy algorithm. So basically, we'll be looking at some of the greedy algorithm. What is greedy algorithm? And this greedy algorithm and graph theory, we'll look at it in line with the difference between that and dynamic programming. And then also we'll tailor that towards graph theory. So we'll be learning, you should understand some of the concepts we learned under trees and graphs, okay, because you apply them, some of the terminologies. If you remember trees and graphs, we talked about some terminology. So try and just understand those terminologies so that when we are doing the concept of greedy algorithms and graph theory, we'll be able to understand them. Okay. All right. Any question? Any question? Any question? Okay. So in the absence of any question, we'll end the class for today. I'll schedule the meeting time for Saturday's class with Theophilus.